Deep within the hidden architecture of our cosmic home, 26,000 light-years away from the pale blue dot we call Earth, an invisible sovereign dictates the gravitational rhythm of 400 billion stars. To reach this central domain, you must traverse a treacherous and beautiful expanse of the Milky Way, diving through spiral arms laced with stellar nurseries, ancient globular clusters, and vast, echoing voids of interstellar space. But as you draw closer to the heart of the galaxy, the environment fundamentally changes. The familiar, sparsely populated neighborhood of our solar system gives way to a suffocatingly dense metropolis of stellar fire. Here, millions of stars are packed into a volume of space so small that if Earth were located in this region, our night sky would be ablaze with the light of a million suns, casting shadows in the dead of night and rendering the surrounding darkness obsolete. Yet, ironically, this brilliant crowded core is completely hidden from our human eyes. Between us and the galactic center lies an impenetrable fortress of cosmic dust and frigid molecular gas, stretching across the parsecs like a dark, heavy blanket. For most of human history, this veil kept the ultimate secret of our galaxy locked away in eternal obscurity. We could look up at the milky band of light sprawling across the summer sky, marveling at its glow, completely unaware that we were staring directly at a monster. At the exact geometric center of this swirling cosmic storm sits Sagittarius A star. It is a supermassive black hole weighing approximately 4 million times more than our Sun, all crushed into a spherical boundary so compact that it could comfortably fit within the orbit of Mercury. Let that scale settle into your mind for a moment. Take the sheer, incomprehensible mass of our Sun, a star so large that 1 million Earths could fit inside it. Now, multiply that unimaginable weight by 4 million. Take all of that matter, all of that fundamental substance, and compress it down until the fabric of space and time simply collapses under the strain, tearing a hole in the universe itself. This is not a solid object. It is a region of pure, unadulterated gravitational tyranny. The boundary of this region is known as the event horizon, the absolute point of no return. Once anything, whether it is a wandering asteroid, a dying star, or a massless photon of light, crosses this invisible threshold, it is severed from the observable universe forever. Inside the event horizon, the known laws of physics shatter into meaningless equations. Time stops moving forward, space folds inward infinitely, and the crushing dark reigns supreme. For decades, theoretical physicists and astronomers operated under a very clear, mathematically rigid assumption about the environment immediately surrounding a supermassive black hole. The rules of gravity dictate that this region must be an absolute wasteland, a cosmic graveyard where nothing delicate could possibly survive, let alone be born. The reason for this lies in a phenomenon known as tidal forces. When an object approaches a mass as profound as Sagittarius A star, the gravitational pull it experiences is not uniform. The side of the object facing the black hole is pulled with a significantly greater force than the side facing away. In the immediate vicinity of a supermassive black hole, this gravitational gradient is so incredibly steep, so violent in its mathematical reality, that it literally stretches matter apart. If a giant cloud of hydrogen gas, the very raw material required to forge new stars, were to drift too close to this gravitational abyss, these tidal forces would shear it to ribbons. The cloud would be spaghettified, stretched into a long, glowing filament of plasma before it ever had the chance to collapse under its own gravity to form a stellar core. In astrophysics, this creates a theoretical exclusion zone, a radius of pure sterilization, where the birth of new stars is explicitly forbidden by the fundamental laws of nature. The math was elegant, it was brutal, and it was universally accepted. Then, the James Webb Space Telescope opened its golden hexagonal eyes and looked deep into the abyss, and the elegant math of the 20th century was thrown into absolute chaos. Unlike its predecessor, the Hubble Space Telescope, which primarily observed the universe in visible and ultraviolet light, James Webb was engineered specifically to see the cosmos in the infrared spectrum. Infrared light is essentially heat radiation, and its longer wavelengths possess a remarkable, almost magical property. They can slip right through the microscopic grains of cosmic dust that block visible light. When James Webb turned its mirrors toward the constellation Sagittarius, it did not just look at the dust, it looked directly through it, piercing the 26,000 light-year veil with unprecedented razor-sharp clarity. What the telescope transmitted back across the void to the screens of astounded scientists on Earth was a profound betrayal of everything we thought we understood about the destructive nature of supermassive black holes. Deep within the forbidden zone, practically brushing against the outer edges of the black hole's gravitational whirlpool, James Webb detected the unmistakable, glowing thermal signatures of protostars. These are not ancient dying stars that accidentally wandered too close to the monster. These are stellar embryos. They are infant stars, still wrapped in their thick, protective cocoons of natal gas and dust, actively gathering mass from their surroundings. They are being born in the exact location where physics dictates they should be shredded into atoms. To understand the sheer absurdity of this discovery, you must imagine trying to delicately assemble a house of cards on the deck of a ship in the middle of a catastrophic Category 5 hurricane. The formation of a star is an incredibly fragile process. It requires a massive cloud of cold molecular gas to remain stable and undisturbed for hundreds of thousands, sometimes millions of years. The gas must slowly, patiently clump together under its own microscopic gravity. The internal temperature must remain freezing cold, allowing the core to grow dense enough, heavy enough, until the immense pressure at the center finally triggers nuclear fusion, igniting a new sun. Any disruption, any sudden shockwave or burst of heat will blow the cloud apart and abort the stellar birth. Yet, right here, in the most violent, turbulent, gravitationally extreme environment in the entire Milky Way, surrounded by the screaming X, rays of the accretion disk and the unyielding tidal shearing of 4 million solar masses, these delicate stellar infants are successfully gestating. This is the paradox of the impossible oasis. How can the ultimate cosmic destroyer simultaneously act as a cradle for new life? What invisible mechanism is shielding these fragile protostars from the crushing forces of the void? Some astronomers suggest that the gas clouds in this region are simply far denser than anything we have ever observed before, packed so tightly that their own internal gravity can briefly rival the pulling power of the black hole. Others theorize that unimaginably strong magnetic fields, twisting and writhing through the galactic center like the skeletal structure of a phantom Leviathan, are creating rigid cages around the gas, holding the stellar nurseries together against the tidal shear. But these are just working theories, frantic attempts to explain a reality that should not exist. The truth is, the supermassive black hole at the center of our galaxy is harboring secrets about the resilience of matter and the tenacity of creation that we are only just beginning to decipher. As we look deeper into this impossible nursery, we realize that the presence of these baby stars is merely the first thread in a much larger, darker tapestry. The monster is not just sheltering life, it is behaving in ways that defy its very nature. It is surrounded by an endless buffet of gas, dust, and stellar winds, a banquet of cosmic proportions. Yet, strangely quietly, the Leviathan is starving. If you are fascinated by the mysteries lurking in the deepest, darkest corners of our universe, and you want to understand why the most powerful object in our galaxy is refusing to eat, make sure to subscribe to the channel and hit the like button. Close your eyes, let the vastness of space wash over you, and prepare yourself, because the deeper we dive into the anatomy of this starvation, the more bizarre the laws of physics will become. To understand the profound paradox of our starving Leviathan, we must first look at the sheer abundance of the cosmic banquet that surrounds it. The central parsec of the Milky Way is not a barren wasteland, nor is it a sterile void stripped clean of matter. On the contrary, it is one of the most chaotic, violently turbulent, and resource-heavy environments in the entire known universe. Swarming around the supermassive black hole is a blinding blizzard of celestial material. There are massive clusters of ancient and newborn stars, such as the arches and quintuplet clusters, which harbor some of the most extreme, hyperactive, and massive stellar bodies ever catalogued by human astronomy. Among these are the Wolf-Rayet stars, gargantuan stellar titans that burn with such ferocious intensity that they are literally tearing themselves apart. These behemoths are locked in a constant, desperate battle against their own gravity, radiating energy so violently that they shed millions of tons of their outer atmospheres into the surrounding space every single second. Their stellar winds roar through the galactic center at velocities exceeding thousands of miles per second, crashing into the winds of neighboring stars, creating vast, sprawling shockwaves that ripple across the dark expanse. The result of all this stellar agony is a sprawling reservoir of superheated plasma, molecular hydrogen, and cosmic dust. It is a swirling ocean of potential fuel. Millions of Earth masses worth of gas are drifting, spiraling, and pooling within the immediate gravitational domain of Sagittarius A star. The monster is essentially drowning in an endless sea of food. It is entirely enveloped by the exact material required to ignite an accretion disk so bright it could outshine the rest of the galaxy combined. And yet, despite being submerged in this limitless ocean of stellar debris, the supermassive black hole is consuming almost nothing. It is sitting at the center of the greatest feast in the Milky Way, slowly starving to death. To quantify this starvation, astrophysicists use a measurement known as the Eddington limit. This is the theoretical maximum rate at which a black hole of a specific mass can consume matter. When a black hole feeds at its Eddington limit, the radiation pressure pushing outward from the superheated, infalling gas perfectly balances the gravitational force pulling that gas inward. It is the absolute limit of celestial gluttony. Active, supermassive black holes in distant, younger galaxies frequently operate near this limit. These objects are known as quasars, and they consume entire solar masses worth of material every single year. The friction within their accretion disks generates temperatures so unfathomable that they emit blinding torrents of ultraviolet light, X-rays, and gamma rays, announcing their violent presence to observers located billions of light-years away across the expanding cosmos. A quasar powered by a black hole the size of Sagittarius A star would dominate our night sky, flooding the Milky Way with lethal, sterilizing radiation and fundamentally altering the evolution of every star system within 1,000 light-years. But our black hole is not a quasar. It is a whisper in the dark. The current energy Uthanch-Fout of Sagittarius A star measures roughly 100 million times less than its theoretical Eddington limit. It is operating at a fraction of its true potential. When astronomers meticulously calculate the actual amount of mass crossing the event horizon of our supermassive black hole, the numbers are almost comical in their insignificance. Sagittarius A star is consuming less than 1/1000th of a solar mass per year. To visualize this agonizingly slow drip of matter, imagine gathering all the gas, dust, and plasma that successfully falls into the black hole over the course of an entire century. If you collected all of that consumed material for 100 years, it would barely equal the mass of a single, unremarkable asteroid. For an object that weighs 4 million times more than our Sun, this is an unimaginably strict starvation diet. At this minuscule rate of consumption, the black hole gains absolutely negligible mass over cosmic timescales. It could sit in this exact state for the entire remaining lifespan of the universe and barely register a change in its gravitational Foot-Han-Forant. This presents one of the most confounding questions in modern astrophysics. Gravity is the ultimate, inescapable force of the universe. It is relentless, it is infinite in its reach, and it only ever pulls. With a mass of 4 million suns, the gravitational well of Sagittarius A star is so deep and so steep that it should effortlessly vacuum up the surrounding oceans of stellar wind and molecular gas. The material is right there, caught in the gravitational web, spiraling inexorably toward the center. So, what invisible force is physically preventing all of this available matter from crossing the final threshold? What is stopping the black hole from eating the feast that is laid out before it? The answer lies deep within the complex, counterintuitive realm of fluid dynamics and thermodynamics, operating under extreme relativistic conditions. The mechanism keeping our monster hungry is something astrophysicists call an Invection-dominated accretion flow. To truly grasp the elegant, bizarre nature of this phenomenon, we must shrink down and follow the harrowing journey of a single microscopic particle of hydrogen gas as it gets caught in the gravitational pull of Sagittarius A star and begins its long, spiraling descent toward oblivion. As our microscopic particle drifts closer to the black hole, it begins to accelerate. The immense gravitational pull acts like an incredibly steep, frictionless cosmic hill. As the particle rolls down this gravitational hill, it exchanges its potential energy for kinetic energy, moving faster and faster, whipping around the black hole at significant fractions of the speed of light. But our particle is not alone. It is surrounded by billions of other particles, all rushing toward the same infinitely small point in space. As this massive volume of gas is funneled into an increasingly tighter, smaller area, the particles inevitably begin to crash into one another. The kinetic energy of their breakneck speed is violently converted into thermal energy through friction. The gas begins to heat up. It heats up to temperatures that shatter the human imagination. In the innermost regions of the accretion flow, just outside the absolute boundary of the event horizon, the temperature of this gas exceeds 100 million degrees. This is a heat far more profound than the core of our sun. At these temperatures, atoms are stripped of their electrons entirely, creating a chaotic, churning soup of naked atomic nuclei and free-flying electrons, a state of matter known as a fully ionized plasma. In a standard, actively feeding black hole like a quasar, this intense heat is a temporary state. The infalling gas in a quasar is incredibly dense, packed tightly together like a crowded city street. Because the particles are so densely packed, they constantly collide. Every time these charged particles collide, they release a tiny burst of energy in the form of a photon, a particle of light. This process is called radiative cooling. The massive cloud of gas bleeds its terrifying heat away into the cold vacuum of space as blinding light. As the gas cools down, it loses its thermal energy, it loses its outward pressure, and it deflates. It flattens out, condensing into a razor-thin, incredibly dense disk that spins beautifully around the black hole's equator. This thin disk is highly efficient. The gas particles rub against each other, lose their orbital momentum through friction, and gracefully slide down the gravitational slope, slipping past the event horizon in a steady, brilliant, catastrophic waterfall of matter. But the environment surrounding Sagittarius A star is fundamentally different. Despite the millions of Earth masses of gas floating in the central parsec, the actual density of the gas in the immediate vicinity of the event horizon is shockingly low. It is a highly diffuse, gossamer-thin mist of plasma. The particles are rushing inward, they are accelerating to millions of miles per hour, and they are heating up to 100 million degrees. But because the gas is so incredibly sparse, the individual particles rarely ever collide with one another. Imagine a handful of hyperactive bees trapped inside an empty cathedral. They are moving at blinding speeds, but the space is so vast that they hardly ever bump into each other. Because these superheated particles are not colliding, they cannot emit photons. Because they cannot emit photons, they have absolutely no way to shed their immense thermal energy. The heat is trapped. The radiative cooling process completely and utterly fails. This failure of cooling is the exact moment the physics of the Invection-dominated accretion flow take over, turning the black hole's own gravitational strength against itself. Because the heat cannot escape as light, it remains locked within the plasma. The laws of thermodynamics dictate that when a gas is heated, it expands. The trapped 100 million degree heat creates an astronomical amount of outward thermal pressure. The gas attempts to explode outward, violently pushing back against the crushing inward pull of the 4 million solar mass black hole. We are witnessing a cosmic arm wrestling match between the two most fundamental forces in nature, the relentless, crushing inward pull of relativistic gravity and the explosive, expansive outward push of extreme thermodynamics. The result of this epic struggle is a bizarre, bloated stalemate. The superheated plasma cannot collapse into the elegant, razor-thin, highly efficient disk seen in active quasars. Instead, the trapped heat causes the entire accretion flow to swell and puff up into a gargantuan, thick, buoyant cloud that resembles a massive, glowing cosmic donut. This puffy structure is utterly inefficient at feeding the black hole. The thermal pressure makes the gas buoyant, like a hot air balloon trying to rise against the pull of the Earth. The plasma wants to float away. The matter technically continues to spiral inward, but it does so with agonizing slowness. Most of the gas simply swirls around endlessly in this bloated, superheated holding pattern, constantly bouncing off the thermal cushion of its own trapped heat. The friction is so low and the outward pressure is so high that the vast majority of the gas never loses enough orbital momentum to actually cross the event horizon. It simply skirts the edge of the abyss, riding the thermal currents, before eventually being flung back out into interstellar space by the chaotic, turbulent eddies of the bloated flow. The black hole is literally choking on the heat of its own meal. The sheer temperature of the infalling gas has created an impenetrable thermal shield that even 4 million solar masses of gravity cannot easily pierce. The energy of the infall is carried or advected along with the sparse particles directly across the event horizon, rather than being radiated away as light, making the entire process practically invisible to optical telescopes. This is the brilliant, frustrating, and incredibly elegant architecture of starvation. Sagittarius. A star is quiet not because there is nothing to eat, but because the physics of extreme heat and low density have conspired to create a perfectly balanced, bloated trap that prevents the food from falling in. It is a celestial titan surrounded by a feast, sitting behind an impenetrable wall of its own trapped burning breath, condemned to a diet of absolute celestial poverty. Yet, this massive, puffed-up, advection-dominated flow is not perfectly smooth, and it is certainly not peaceful. If you stare long enough into the data returned by the most sensitive X-ray and infrared observatories, you will notice that this quiet, starving monster occasionally twitches. While the massive, puffy donut of gas largely refuses to fall in, the structure is racked by intense internal violence. There are chaotic magnetic fields threading through this 100 million degree plasma, twisting and winding themselves into impossible knots. There are cold, dense clumps of gas like heavy cosmic raindrops attempting to navigate the superheated fog. Several times a day, this fragile, bloated equilibrium shatters. The black hole suddenly flashes, flaring up with a sudden, violent burst of X-rays and infrared radiation that lasts for a few fleeting hours before fading back into the creeping, hungry dark. If the black hole is blocked by this impenetrable thermal cushion, how is anything getting through? What is the physical trigger behind these mysterious, daily flashes of light? If you find yourself drifting deeper into the mechanics of this cosmic abyss, completely mesmerized by the strange, counterintuitive physics that govern the dark heart of our galaxy, take a moment to subscribe, leave a like, and let your mind float freely into the void. Rest your eyes, focus on the slow, rhythmic breathing of the universe, and prepare yourself, because the mystery of the bleeding spirals and the daily flashes of the Leviathan is about to pull us even closer to the event horizon. To unravel the mystery of the Leviathan's sudden, daily flashes of light, the enigmatic hiccups of a starving 4 million solar mass black hole, we must descend even further into the chaotic architecture of its immediate surroundings. The advection, dominated accretion flow, that bloated, superheated cushion of plasma, resisting the inward pull of gravity, is not a static, uniform balloon of gas. If you were to look at it with the unprecedented dust-piercing infrared vision of the James Webb Space Telescope, you would not see a smooth, featureless halo. Instead, you would witness a terrifyingly turbulent, churning vortex. The environment within the central light year of Sagittarius, a star is a violent, unstable battleground governed by extreme fluid dynamics and tangled, writhing magnetic fields. Within this superheated fog, astronomers have mapped out a sprawling, complex structure known as the mini-spirals. These are not the grand, majestic, star-studded spiral arms that define the sweeping shape of the Milky Way itself. These mini-spirals are distinct, localized streams of ionized gas, primarily hydrogen and helium, that are physically plunging toward the galactic center. They are the immediate tributaries feeding the central abyss. For decades, based on lower resolution radio and infrared observations, Astrophysicists modeled these mini spirals as smooth, continuous rivers of plasma. They assumed the gas flowed along graceful, predictable orbital paths, gradually bleeding off angular momentum and trickling down toward the event horizon in a steady, albeit painfully slow, stream. It was a neat, mathematically convenient picture of celestial mechanics. But James Webb's astonishing resolution shattered this illusion of smoothness. When the telescope peeled back the layers of thermal emission, it revealed that the mini-spirals are not continuous rivers at all. They are jagged, fragmented, and profoundly clumpy. The material within these spiral arms is highly unevenly distributed, forming dense, distinct concentrations of matter embedded within the thinner, faster, moving streams of gas. Astronomers refer to this phenomenon as clumpy accretion. Instead of a smooth, homogeneous flow, the black hole is being fed by a chaotic bombardment of discrete, heavy cosmic clumps. These clumps are not insignificant. Some of them measure hundreds of astronomical units across comparable to the entire span of our solar system, from the Sun out past the orbit of Neptune, yet they are compressed into incredibly dense knots of plasma by the sheer pressure of their environment. They contain enough mass to produce distinct, measurable spectral signatures in Webb's data. And it is the perilous journey of these dense clumps that provides the key to understanding the black hole's daily flashes. Imagine one of these massive, dense knots of gas breaking away from the main body of a mini-spiral and beginning its final spiraling plunge towards Sagittarius, a star. Unlike the diffuse, gossamer, thin plasma of the bloated accretion flow, which is held aloft by its own trapped thermal pressure, this clump is dense enough, heavy enough, and cohesive enough to briefly punch through the thermal cushion. It is like a heavy rock dropped into a thick vat of boiling syrup. The clump maintains its structural integrity as it accelerates down the steepening gravitational gradient, whipping around the black hole at terrifying velocities approaching a significant fraction of the speed of light. As it plunges deeper into the gravitational well, entering the innermost accretion zone just outside the event horizon, the environment becomes unimaginably hostile. The tidal forces, the exact same forces that should, theoretically, tear apart the protostars we discovered earlier, begin to act upon the clump with devastating effect. The side of the gas knot closest to the black hole is yanked inward with significantly greater force than the trailing side. Simultaneously, the clump is subjected to extreme magnetic friction as it plows through the tangled, chaotic magnetic fields threading the central region. The immense gravitational energy of the infall, combined with the brutal mechanical compression of the tidal forces and the drag of the magnetic fields, violently heats the clump in a matter of hours. This is not the slow, trapped heating of the diffuse advection flow. This is a rapid, cataclysmic spike in temperature. The gas within the clump is flash, heated to temperatures far exceeding the ambient 100 million degree plasma. As the clump is finally ripped apart by the tidal shear, smeared into a glowing, superheated streak of plasma right on the edge of oblivion, it releases a sudden, brilliant burst of energy. This violent, localized release of gravitational and thermal energy is what we observe from Earth as a flare. For a few fleeting hours, the luminosity of Sagittarius A star spikes dramatically. Detectors in orbit around our planet register sudden surges in X, ray, and near-infrared radiation. The black hole briefly awakens, shining 10 to 100 times brighter than its baseline quiescent state. Then, as the shredded remnants of the clump either slip across the event horizon or are violently flung outward by magnetic slingshots, the energy dissipates, the light fades, and the monster returns to its quiet, starving slumber. This clumpy accretion model beautifully explains the erratic, unpredictable nature of the black hole's activity. The flares are not the result of a steady, continuous feeding process. They are the cosmic equivalent of hiccups, sudden, violent reactions to the ingestion of large, distinct, hard-to-swallow chunks of matter. The black hole is starving, but every few hours, a dense clump of plasma manages to navigate the turbulent thermal cushion and delivers a concentrated dose of mass to the inner accretion zone, triggering a fleeting, explosive burst of light. But the physical violence of these clumpy accretion flares is only half of the story hidden within the mini spirals. James Webb spectroscopic instruments, specifically the mid-infrared instrument, or MIRI, were designed not just to take pictures, but to dissect the very chemical composition of the universe. By analyzing the exact wavelengths of light absorbed and emitted by the gas near the galactic center, Webb functions as a cosmic laboratory, revealing the atomic and molecular makeup of the environment with astonishing precision. When astronomers aimed MIRI's spectrometers at the dense, clumpy regions of the mini spirals, looking for the standard signatures of superheated hydrogen and carbon, they found something deeply unsettling. Mixed in with the roaring 100 million-degree plasma, the howling stellar winds, and the crushing tidal forces, the telescope detected the unmistakable, fragile spectral signature of water vapor. The detection of intact H2O molecules within fractions of a light year from a 4 million solar mass black hole is, from a purely chemical standpoint, an absolute absurdity. Water molecules are notoriously delicate. The chemical bonds holding the oxygen and hydrogen atoms together are easily shattered by high-energy radiation. In the immediate vicinity of Sagittarius A star, the environment is flooded with extreme ultraviolet light and X, rays both from the occasional flares of the black hole itself and from the massive hyperactive Wolf-Rayet stars dominating the central parsec. In a normal astrophysical environment, if you were to expose a cloud of water vapor to this level of intense ionizing radiation, the molecules would be instantly destroyed. The process, known as photodissociation, acts like a microscopic hammer, smashing the molecular bonds apart in a matter of hours, reducing the water to its constituent oxygen and hydrogen atoms, or producing highly reactive hydroxyl radicals. Maintaining a stable, detectable abundance of water vapor in this cosmic slaughterhouse should be physically impossible. The radiation environment is simply too harsh. The destruction rate should vastly outhands any natural formation process. Yet the data from James Webb is unequivocal. The water is there. This impossible chemical oasis forces astrophysicists to confront two radically different, equally mind-bending possibilities. The first possibility is that we are drastically underestimating the structural complexity of the dense clumps within the mini spirals. If these clumps are not just dense but hyper-dense, possessing a column density of gas and dust, thick enough to act as a physical shield, they might be capable of protecting their innermost cores from the searing ultraviolet radiation. The outer layers of the clump would take the brunt of the radiation damage, constantly being stripped away and ionized, while the deep interior remains relatively cool and chemically stable. Within these heavily shielded, microscopic safe havens, complex molecules like water could survive indefinitely, hidden away in the dark, dense hearts of the plunging gas knots. The second, perhaps more profound possibility involves continuous, hyperactive cosmic chemistry. If the water is not being shielded, then it must be produced at a staggering rate, a rate fast enough to constantly replace the molecules being destroyed by the radiation. But how do you synthesize water in the middle of a relativistic vortex? The answer might lie in the very violence of the environment. The galactic center is battered by an extraordinarily high flux of cosmic rays, protons, and atomic nuclei, accelerated to near light speed by supernova and magnetic reconnection events. When these high-energy particles slam into the surrounding gas and dust grains, they act as powerful chemical catalysts. They break existing bonds and force new ones to form, driving complex, high-temperature chemical reactions that would be far too slow to occur in typical interstellar space. The constant shock waves from stellar winds colliding with the accretion flow could also compress the gas, suddenly raising the temperature and triggering rapid chemical synthesis. The galactic center might be functioning as a massive, brutal chemical factory, using the sheer violence of shock waves and cosmic ray bombardment to continuously forge delicate water molecules out of the surrounding chaos, maintaining a fragile, dynamic equilibrium between creation and destruction. The implications of this water vapor are staggering, and they loop us back to the very first, most shocking discovery made by James Webb, the impossible nursery of protostars. Water is not just a chemical curiosity, it is a vital thermodynamic tool. In the harsh environments of space, gas clouds struggle to cool down. As gravity tries to compress a cloud to form a star, the cloud naturally heats up, increasing its internal pressure and resisting further collapse. For star formation to proceed, the cloud must have a way to efficiently radiate that heat away into space. This is where water becomes essential. Water molecules are highly efficient radiators of infrared energy. When a water molecule is excited by collisions in a warming gas cloud, it easily sheds that energy by emitting an infrared photon. If dense, shielded clumps within the mini spirals are harboring significant amounts of water vapor, this water acts as a powerful cosmic coolant. It allows the dense gas within the clump to shed its internal heat incredibly fast. As the clump rapidly cools, its internal thermal pressure drops, allowing gravity to take over with devastating speed. The clump can undergo catastrophic gravitational collapse, condensing into a protostellar core before the tidal forces of the black hole have a chance to rip it apart. The presence of water vapor provides the crucial missing link. It explains how the impossible oasis exists. The same hyper-dense clumps that shield the delicate water molecules from the searing radiation also utilize that water to rapidly cool down, enabling the lightning, fast birth of new stars right on the precipice of the event horizon. The supermassive black hole is not just a destroyer. Through the chaotic, clumpy nature of its accretion flow and the extreme shock-driven chemistry it generates, it is inadvertently providing the exact thermodynamic conditions necessary to forge new life in the darkest, most hostile environment imaginable. As we pull back from the microscopic chemistry of water vapor and the localized violence of the daily flares, the true scale of the galactic center's complexity begins to emerge. The monster is starving, yet it burps light daily. It is a region of absolute destruction, yet it harbors the fragile building blocks of life and the chaotic birth of new stars. But this is only the visible ecosystem. What if I told you that lurking just beyond the glare of the accretion disk, hidden in the dense, chaotic swarm of the central parsec, are invisible predators, nomads of profound mass, silently drifting toward the ultimate abyss, waiting to be consumed? If you are captivated by the intricate, terrifying mechanics of our supermassive black hole and want to uncover the invisible ghosts haunting the galactic core, subscribe now and hit the like button. Let the silence of the void surround you. Take a deep breath and prepare to meet the missing links of the dark ecosystem. Stepping back from the microscopic miracles of water vapor and the localized violence of the bloated accretion flow, we must cast our gaze slightly outward into the suffocatingly crowded, chaotic swarm of the central parsec. The immediate vicinity of Sagittarius A star is not merely a hostile nursery or a starving mouth. It is the ultimate cosmic drain. Everything in the galaxy that possesses enough mass and loses enough momentum is destined to eventually sink into this dark abyss. And lurking within this swirling gravitational sinkhole, hiding in plain sight among the millions of blindingly bright hyperactive stars, are the ultimate phantoms of astrophysics. These are the missing evolutionary links of the universe, invisible predators silently drifting through the stellar metropolis, waiting for their inevitable catastrophic reunion with the central Leviathan. We are looking for intermediate mass black holes, the dark nomads of the galactic ecosystem. To understand the profound significance of these invisible wanderers, you must first understand the glaring, frustrating gap in our comprehension of black hole evolution. For decades, astronomers have been able to confidently categorize black holes into two distinct, wildly different weight classes. On one end of the spectrum, we have stellar mass black holes. These are the relatively tiny, ubiquitous remnants of dead stars. When a star, roughly 10 to 20 times the mass of our sun, exhausts its nuclear fuel, its core collapses under its own weight, forging a black hole that typically weighs between 3 and 10 solar masses. These are scattered by the millions throughout the Milky Way, silent cosmic graves marking the sites of ancient supernovae. On the other extreme end of the spectrum, we have the supermassive behemoths like Sagittarius A star, weighing millions or even billions of times the mass of our sun, reigning supreme at the centers of nearly all large galaxies. But between these two extremes lies a massive, baffling void. Where are the teenagers? Where are the black holes weighing 100, 1,000, or 100,000 solar masses? Mathematics and the fundamental models of cosmic evolution demand that these intermediate mass black holes must exist. Supermassive black holes could not have simply popped into existence at the dawn of the universe fully formed, weighing millions of solar masses. They had to grow. They had to start as smaller seeds and consume vast amounts of matter, or they had to merge with other black holes of substantial size over billions of years. This process of hierarchical assembly requires a vast population of intermediate mass black holes acting as the essential building blocks. Yet, actually finding one of these mid-sized monsters in the vast expanse of the cosmos has proven to be one of the most maddening challenges in modern observational astronomy. The reason these intermediate black holes are so elusive is directly tied to their size and their environment. A stellar mass black hole is often found in a binary system, locked in a tight orbit with a living star. As it strips gas away from its companion, that stolen gas forms a miniature accretion disk, glowing brightly in X-rays and betraying the black hole's location. A supermassive black hole sits at the center of a galaxy, surrounded by a virtually infinite supply of interstellar gas and entire star clusters, giving it ample opportunity to feed and announce its presence. But an intermediate mass black hole is a lonely wanderer. It is too massive to have easily formed from a single star, meaning it likely does not have a convenient companion star to feed upon. And unless it happens to be plunging directly through a dense molecular cloud, it spends its existence drifting through the empty, frigid vacuums of interstellar space, consuming absolutely nothing. Without an accretion disk of superheated gas to emit radiation, a black hole is perfectly, flawlessly black. It emits no light, it casts no shadow against the empty void, and it remains utterly undetectable to traditional telescopes. But the central parsec of the Milky Way changes the rules of the game. This region is not empty interstellar space. It is a suffocatingly dense environment, packed with gas, dust, and millions of stars. If an intermediate mass black hole were to wander into this chaotic arena, it could not remain entirely hidden. Its immense gravity would betray it, warping the orbits of nearby stars and pulling in localized shrouds of warm dust. And the fundamental laws of orbital mechanics guarantee that if these invisible nomads exist anywhere in our galaxy, they are inexorably being dragged down into this exact central region. The mechanism responsible for dragging these dark nomads into the jaws of Sagittarius A star is a profound physical process known as dynamical friction. This is not friction in the traditional sense. There is no physical rubbing of surfaces, no atmospheric drag. Dynamical friction is a purely gravitational phenomenon, and it acts as the inescapable undertow of the galactic ocean. Imagine a heavy, invisible bowling ball rolling through a vast, three-dimensional sea of suspended marbles. As the massive black hole plows through the dense stellar field of the galactic center, its intense gravity tugs at every single star it passes. The black hole is moving fast, so it flies past these stars before it can pull them all the way in. However, its gravitational pull slightly alters the trajectory of every star it encounters, yanking them inward and backward as it passes by. This continuous, sweeping gravitational tug creates a localized traffic jam of stars in the space immediately behind the moving black hole. A dense, invisible wake of stellar mass forms, trailing the black hole like the churning water behind a massive ship. Because this trailing wake represents a concentrated clump of mass, it exerts its own collective gravitational pull. It pulls backward on the moving black hole. This backward gravitational drag constantly saps the black hole of its orbital kinetic energy. Over millions of years, as the black hole slowly bleeds away its forward momentum, its orbit decays. It begins to spiral inward, sinking deeper and deeper into the ultimate gravitational well. Dynamical friction ensures that the most massive objects in any stellar environment will always, inevitably, sink to the very bottom. And the absolute bottom of the Milky Way is the event horizon of Sagittarius A star. But where do these sinking invisible nomads come from in the first place? Astrophysicists point to two primary, equally violent origin stories. The first involves the oldest, most tightly packed structures in our galaxy, the globular clusters. These are ancient, spherical cities containing hundreds of thousands of stars, orbiting in the halo of the Milky Way. Within the suffocatingly dense cores of these clusters, a terrifying process known as runaway core collapse can occur. Through the same mechanism of dynamical friction, the heaviest stars in the cluster sink to the absolute center. Packed so tightly together that their outer atmospheres practically touch, these massive stars begin to collide. They smash into one another, merging to form a gargantuan, unstable Frankenstein star weighing hundreds of times more than our Sun. This unnatural behemoth burns through its nuclear fuel in a geological heartbeat and collapses under its own immense weight, forging a pristine intermediate mass black hole. Over billions of years, the gravitational tidal forces of the Milky Way can slowly rip these globular clusters apart, scattering their stars into the galactic halo, but leaving the heavy, dark core behind. Stripped of its stellar city, the intermediate mass black hole begins its long, lonely, spiraling descent toward the galactic center. The second origin story involves an even larger scale of cosmic violence: galactic cannibalism. The Milky Way is a predator. It has grown to its massive size over 13 billion years by mercilessly hunting down, tearing apart, and consuming smaller dwarf galaxies. When a dwarf galaxy falls into the gravitational grip of the Milky Way, it is subjected to brutal tidal shearing. The outer layers of the dwarf galaxy, consisting of gas and millions of stars, are ripped away, stretched into long, winding streams of debris that wrap around our galaxy like ribbons. But at the heart of that dying dwarf galaxy lies its own central black hole, likely an intermediate mass object weighing tens of thousands of solar masses. Once the dwarf galaxy is entirely digested, its naked, dark heart is left wandering through the Milky Way. And just like the remnants of the globular clusters, the inescapable undertow of dynamical friction seizes this orphaned black hole, dragging it relentlessly down into the central parsec. For decades, these origin stories and the physics of dynamical friction remained purely theoretical. Astronomers knew that intermediate mass black holes should be sinking into the center of the galaxy, but proving their existence in a region already blinded by cosmic dust and the blinding glare of millions of stars was seemingly impossible. Ground-based infrared telescopes simply lacked the sensitivity and resolution to separate a tiny, warm dust cloud enveloping a dark nomad from the overwhelmingly chaotic background. Then, the James Webb Space Telescope turned its golden mirrors toward the abyss, and the ghosts finally began to materialize. Webb cannot see the black holes themselves, but its unprecedented mid-infrared sensitivity allows it to see the localized thermodynamic chaos they create. As an intermediate mass black hole sinks through the dense gas and dust of the central parsec, its gravity captures a small, localized shell of material. This material does not form a massive blazing accretion disk like a quasar, but it does become compressed and heated as it swirls around the invisible nomad. This localized heating creates a microscopic, warm cocoon of dust that glows faintly in very specific mid-infrared wavelengths. When astronomers meticulously analyzed the high-resolution images provided by Webb's near-infrared camera and mid-infrared instrument, filtering out the blinding light of the millions of normal stars, they found anomalies. They detected several distinct, incredibly compact point sources of infrared light that simply did not behave like stars. They lacked the expected spectral absorption lines that indicate a stellar atmosphere. Even more suspiciously, when astronomers tracked the movement of these anomalous point sources over time, comparing Webb's data with archival observations, they realized these objects were moving with trajectories and velocities that were fundamentally wrong for low-mass objects. The mathematical physics of their orbits strongly suggested they possessed masses ranging from several hundred to several thousand times that of our Sun. Yet, they emitted absolutely no visible light and no significant X-rays. They were perfectly dark, massive, compact objects cloaked in microscopic shrouds of warm dust. These are the strongest candidates ever discovered for intermediate mass black holes. They are the missing links of the dark ecosystem, finally exposed by the unparalleled dust-piercing vision of James Webb. The discovery of these dark nomads wandering within the central light years of the galaxy carries profound, staggering implications for the future of our cosmic neighborhood. They are not merely orbiting the central Leviathan in stable harmony, they are actively sinking. Dynamical friction is currently bleeding away their final reserves of orbital energy. This means we are looking at the raw ingredients for future cosmic cataclysms. When one of these intermediate mass black holes finally reaches the end of its agonizing spiral and crosses the event horizon of Sagittarius A star, the resulting collision will not produce a flash of light. A black hole merging with another black hole is an entirely dark event, but it is an event of such unfathomable violence that it will literally ripple the fabric of the universe. The merger will convert a fraction of the total mass directly into pure gravitational wave energy, sending distortions in space and time racing outward at the speed of light. These ripples will pass right through the cosmic dust, through the Earth, and through our very bodies, completely unimpeded. The presence of these sinking nomads confirms the long-held theory of hierarchical assembly. It proves that the monster at the center of our galaxy is not a static, unchanging entity. It is an active predator that has grown and continues to grow by cannibalizing its own dark children. The central parsec is a graveyard where the dead cores of ancient star clusters and the cannibalized hearts of dwarf galaxies are dragged into the dark, waiting to be consumed. The silence of Sagittarius. A star is a deception. It may be starving for gas, but it is preparing to swallow entire black holes. The ecosystem surrounding the supermassive black hole is proving to be infinitely more complex, dangerous, and populated than anyone dared to imagine. We have seen the impossible stellar nurseries clinging to life on the edge of destruction. We have witnessed the bloated, starving accretion flow coughing up daily flares of violent light. And now, we have uncovered the invisible, sinking nomads, the missing links of black hole evolution, drifting like phantoms through the suffocating stellar fog. But these phantoms do not drift through empty space. They are pushing their way through the most violently crowded, unforgiving stellar environment in the entire galaxy. A place where 10 million stars are trapped in an endless, chaotic demolition derby. If the mechanics of this dark ecosystem have captured your imagination, and you want to witness the sheer kinetic violence of a star cluster where collisions are not just possible, but inevitable, hit that subscribe button, leave a like to support the channel, and prepare yourself. We are about to step out of the invisible shadows and directly into the blinding, chaotic crossfire of the central parsec. Stepping out of the invisible, creeping shadows cast by the sinking dark nomads, we are thrust violently into the blinding, chaotic glare of the visible galactic core. The intermediate mass black holes do not drift through a quiet, empty void. They must push their way through the most heavily populated, aggressively congested, and physically unforgiving environment in the entire Milky Way. This is the central parsec, a region of space that fundamentally redefines our understanding of stellar density and orbital mechanics. To truly grasp the sheer claustrophobic terror of this environment, we must first look at our own quiet corner of the galaxy and then brutally compress it. Our sun exists in a relatively peaceful suburban neighborhood of the Milky Way. If you look up at the night sky from Earth, the closest star to our solar system is Proxima Centauri, sitting quietly in the dark about 4 light-years away. In the vast, empty volume of space stretching between our Sun and Proxima Centauri, there is absolutely nothing but a few wisps of interstellar gas, some wandering comets, and the cold vacuum of the cosmos. It is a distance so vast that even light, the fastest entity in the universe, takes 4 years to cross it. Our Sun enjoys an almost unimaginable degree of personal space, allowing our planets to orbit in perfect, undisturbed harmony for billions of years. Now take that exact same volume of space, that 4 light-year bubble spanning from the Sun to Proxima Centauri, and physically transport it to the central parsec surrounding Sagittarius A star. In that exact same amount of space, nature has aggressively packed roughly 10 million individual stars. Let that terrifying density sink into your mind. 10 million raging, burning nuclear furnaces confined within a space where we currently only have one. If the Earth were somehow transported into the middle of the central parsec, the concept of nighttime would completely cease to exist. The sky would be a solid, blinding dome of stellar fire. Hundreds of thousands of stars would appear as bright as the full moon, casting sharp, overlapping shadows in every conceivable direction. The ambient radiation would be so intense, so overwhelmingly powerful, that the atmosphere of our planet would be instantly boiled away into space, and the oceans would vaporize in a matter of hours. This is not a star cluster. It is a hyper-dense, boiling cauldron of stellar mass, held together by the terrifying gravitational anchor of the 4 million solar mass monster lurking at its exact geometric center. Because of this suffocating proximity, the stars in the central parsec do not follow the graceful, solitary circular orbits that we are familiar with in the outer spiral arms of the galaxy. They are trapped in a high-speed, chaotic, and relentlessly violent demolition derby. The immense gravitational pull of the supermassive black hole acts as a cosmic accelerator, whipping these 10 million stars around at velocities that defy human comprehension. Stars near the center do not gently drift. They scream through the void at speeds exceeding millions of miles per hour. As they race along their elliptical overlapping trajectories, they are constantly influenced by the gravitational tugs of their millions of neighbors. Every close pass, every near miss, slightly alters a star's trajectory, sending it veering onto a new, unpredictable path. The orbital mechanics here are a nightmare of mathematical chaos, a constantly shifting, multi-body problem where long-term stability is an absolute physical impossibility. In an environment this densely packed and this incredibly fast, the most extreme events in astrophysics transition from being rare statistical anomalies to absolute, unavoidable certainties. In the quiet suburbs of the galaxy, the idea of two stars physically colliding is almost mathematically impossible. Space is simply too vast, and the targets are too small. But in the suffocating crush of the central parsec, stellar collisions are a terrifying routine reality. When you have 10 million objects screaming through a confined space at fractions of the speed of light, their paths will eventually, inevitably, intersect. Imagine the sheer, apocalyptic violence of two main sequence stars, each weighing more than our Sun, colliding head-on at 3 million miles per hour. This is not a solid impact like two planets crashing together. Stars are massive spheres of superheated fusing plasma. When they collide, their outer atmospheres slam into one another with such catastrophic kinetic energy that a massive shockwave ripples outward, violently ejecting millions of tons of burning plasma into the surrounding interstellar medium. As the two stellar bodies plow deeper into one another, their intense magnetic fields violently twist and snap, releasing blinding flares of X-ray and ultraviolet radiation. The two superheated cores where the nuclear fusion actually takes place finally meet and merge. The sudden, violent addition of mass and fresh hydrogen fuel forces the newly merged core to dramatically accelerate its fusion rate. The resulting object is a Frankenstein star, a monstrous, stitched-together stellar hybrid that burns far hotter, brighter, and bluer than either of its original components. Astronomers call these merged anomalies blue stragglers because they appear deceptively young and hot, straggling behind the normal aging process of the surrounding stellar population. The central parsec is heavily populated with these deceptive, violently forged hybrids, masquerading as newborn stars when they are actually the resurrected glowing corpses of catastrophic head-on collisions. But a direct, head-on collision is just one extreme outcome of this chaotic stellar traffic jam. Far more common and perhaps far more bizarre are the violent near misses. Because the density is so high, stars frequently pass within agonizingly close proximity to one another without actually touching cores. However, at these microscopic cosmic distances, the gravitational tidal forces become absolute weapons of destruction. If a smaller, less dense star passes too close to a massive giant star, the larger star's gravity will physically reach out and grab the smaller star's outer atmosphere. In a process known as tidal stripping, the giant star will violently tear away the outer layers of plasma from its smaller neighbor, siphoning off its mass in a glowing, spiraling bridge of stolen fire. If a star has the supreme misfortune of passing too close to the supermassive black hole itself, but just outside the radius of total destruction, the tidal stripping reaches an apocalyptic extreme. The black hole's gravity is so profoundly steep that it can completely peel a star like an orange. It violently shreds and consumes the entire outer atmosphere, the corona, the chromosphere, and the massive convective layers, pulling them away in a screaming torrent of superheated gas. But remarkably, the incredibly dense, incredibly hot nuclear core of the star manages to survive the encounter, shooting past the black hole and escaping back into the cluster. What remains is a stripped stellar core. It is a naked, exposed nuclear reactor, radiating intense ultraviolet light and drifting through the cluster without its protective atmospheric shell. James Webb's unprecedented infrared resolution has detected numerous anomalous objects in the central parsec that perfectly match the profile of these naked cores, serving as glowing, spectral monuments to the brutal, unforgiving nature of near-miss tidal encounters. Yet, of all the chaotic, violent interactions that occur within this stellar demolition derby, none are more dramatic, more mathematically precise, or more profoundly consequential than the mechanism responsible for creating hypervelocity stars. To understand this extraordinary phenomenon, we must focus on a specific type of stellar arrangement that is incredibly common throughout the universe: the binary star system. In a typical binary system, two stars are locked in a perpetual gravitational waltz, orbiting a shared center of mass. They are bound together by their mutual gravity, spinning through the void as a single combined unit. When a binary star system is unlucky enough to have its orbit disturbed by the chaotic traffic of the central cluster, it can find itself on a terrifying, plunging trajectory aiming directly toward Sagittarius A star. As the two dancing stars accelerate down the steepening gravitational well, moving faster and faster toward the dark abyss, their mutual gravitational bond is put to the ultimate test. They are clinging to one another, spinning rapidly, while the supermassive black hole reaches out with a tidal force that grows exponentially stronger with every passing second. There is a highly specific, mathematically defined boundary surrounding the black hole known as the tidal disruption radius for a binary system. This is the exact microscopic threshold where the gravitational pull of the 4 million solar mass monster finally exceeds the mutual gravitational bond holding the two stars together. When the spinning binary system crosses this invisible line, the physical consequences are instantaneous and unimaginably violent. The mechanism that takes over is known as the Hills mechanism, named after the astrophysicist who first theorized it, and it functions as the most powerful gravitational slingshot in the entire universe. As the binary pair crosses the threshold, the black hole's tidal shear aggressively grabs the star that happens to be positioned slightly closer to the event horizon. It violently halts that star's forward momentum, ripping it away from its partner with brutal mechanical efficiency. This captured star is suddenly violently decelerated, its kinetic energy bled away in an instant. It falls into a tight, terrifyingly fast, highly elliptical orbit around the supermassive black hole. It is permanently trapped, doomed to spend the rest of its existence whipping around the Leviathan in a desperate high-speed orbit, becoming part of the famous S star cluster that astronomers like Andrea Ghez and Reinhard Genzel spent decades tracking. But the fate of the second star, the partner that was positioned slightly further away from the black hole at the exact moment the bond snapped, is entirely different. According to the absolute laws of physics and the conservation of energy, the massive amount of orbital energy that was violently stripped away from the captured star cannot simply disappear. It must be instantly, perfectly transferred to the escaping partner. In a fraction of a second, the second star is injected with a dose of kinetic energy so massive that it defies comprehension. The gravitational bond holding the binary together acts like a tensioned rubber band. When the black hole snaps that band, the outer star is violently launched outward, accelerating away from the galactic center at speeds that break all the rules of normal stellar motion. This star is instantly transformed into a hypervelocity star. It screams away from the supermassive black hole at velocities exceeding 2 to 3 million miles per hour. This speed is so profoundly fast that it completely shatters the galactic speed limit. Normally, the combined gravitational pull of the entire Milky Way galaxy, the hundreds of billions of stars, the dark matter halo, and the central black hole itself exerts an escape velocity. If a star wants to physically leave the galaxy, It must be traveling fast enough to overcome the pull of all that mass. For a star located near the galactic center, that escape velocity is immense. But the Hill's mechanism is so violently efficient, and the energy transfer is so extreme, that the hypervelocity star is launched with more than enough speed to completely sever its gravitational ties to the Milky Way. The hypervelocity star becomes a cosmic exile. It blasts outward through the dense central parsec, tearing through the spiral arms and crossing the vast, empty expanses of the galactic halo. It will never stop. It will never slow down enough to be pulled back. It is destined to physically exit the Milky Way galaxy entirely, flying out into the unimaginably vast, pitch-black, freezing void of intergalactic space. It will spend the rest of its long, lonely life burning its nuclear fuel in the absolute dark, a solitary beacon drifting endlessly between the galaxies, carrying within its core the chemical signature of the chaotic, violent demolition derby where it was born. When astronomers point their telescopes out toward the edges of the Milky Way and detect these hypervelocity stars screaming outward into the void, they are not just looking at fast-moving objects. They are looking at the direct, undeniable forensic evidence of the supermassive black hole's raw mechanical power. Every hypervelocity star is a messenger, a ballistic projectile violently ejected from the central parsec, proving that the Hill's mechanism is actively operating deep within the blinding glare of the core. The ecosystem surrounding Sagittarius A star is a place of absolute extremes. It is a nursery for impossible protostars, a graveyard for invisible intermediate mass black holes, and a chaotic, high-speed demolition derby where stars are forced to collide, merge, strip one another naked, and slingshot each other into the intergalactic void. We have dissected the mechanics of this terrifying environment, pulling back the curtain on the physical laws that govern the darkest, most crowded corner of our cosmic home. But how did we actually figure all of this out? How did humanity, trapped on a tiny rock 26,000 light-years away, manage to pierce the impenetrable wall of cosmic dust and map the chaotic orbits of these screaming stars? If you are captivated by the sheer ingenuity required to solve the greatest mysteries of the universe, and you want to understand the century-long technological war astronomers waged against the cosmic fog, hit that subscribe button, leave a like, and stay with me. The story of how we opened our eyes to the abyss is just as thrilling and just as fraught with impossible challenges as the monster itself. Let the vastness of the cosmos settle in your mind, and prepare to embark on the century of blindness. To truly appreciate the sheer, terrifying magnitude of the discoveries unfolding in the central parsec, we must briefly step back from the blinding glare of the stellar demolition derby and confront the profound isolation of our own vantage point. We are perched on a small rocky planet orbiting an unremarkable yellow dwarf star situated within the Orion Spur, a minor spiral arm located roughly halfway between the galactic center and the desolate outer rim of the Milky Way. When we look up into the night sky on a clear, dark summer evening, away from the suffocating light pollution of human cities, we can see the magnificent, glowing band of our galaxy arching across the heavens. But if you look closely at that glowing band, particularly in the direction of the constellation Sagittarius, you will notice massive, sprawling patches of absolute darkness. These dark voids, historically referred to as the Great Rift, are not empty spaces where stars have failed to form. They are something much more formidable. They are colossal, towering walls of interstellar soot, microscopic silicate grains, and dense, freezing molecular gas. This cosmic fog stretches across 26,000 light-years of space, standing as an impenetrable fortress between our solar system and the gravitational sovereign that rules us. If this vast ocean of intervening dust were somehow magically swept away, the night sky as we know it would be fundamentally transformed. The sheer concentration of stellar fire in the central parsec is so incredibly brilliant that the galactic center would blaze in our sky with a luminosity outshining the full moon. It would cast sharp, distinct shadows on the surface of the Earth, fundamentally altering the evolutionary trajectory of nocturnal life and rewriting the mythologies of every human civilization. But the dust remains. Visible light, the spectrum of electromagnetic radiation that our human eyes evolved to detect, simply cannot penetrate this dense cosmic fog. The wavelengths of visible light are too short. When they encounter the microscopic dust grains, the photons are scattered, absorbed, and completely extinguished long before they can traverse the 26,000 light-year journey to our retinas. For the vast majority of human history, from the moment our ancestors first looked up at the stars to the dawn of the 20th century, this physical limitation created a profound, absolute blindness. We were circling a 4 million solar mass monster, bound to it by an unbreakable gravitational chain, completely unaware of its existence. We were living in the century of blindness. Because we could not see the heart of our galaxy, we had to wait until we learned how to listen to it. The first tear in the cosmic veil did not come from a telescope pointing at the sky, but from a strange, rotating contraption of brass, wood, and Ford Model T tires built in a potato field in New Jersey. The year was 1932, and a young physicist named Carl Jansky was working for Bell Telephone Laboratories. Jansky was not an astronomer. He was a radio engineer tasked with a highly practical, earthly problem. The newly established transatlantic radio telephone service was being plagued by mysterious bursts of static, and Jansky was ordered to build an antenna to track down the source of this disruptive noise. He constructed a massive directional antenna array that could rotate a full 360 degrees, earning it the affectionate nickname of Jansky's merry-go-round. For months, Jansky meticulously cataloged the static. He identified the crashing sounds of nearby thunderstorms and the distant rolling echoes of lightning strikes occurring across the globe. But hiding beneath the terrestrial noise, Jansky's sensitive equipment detected something else. It was a faint, steady, relentless hiss. Unlike the chaotic crackle of weather, this hiss was rhythmic, predictable, and profoundly strange. Jansky noticed that the signal peaked in intensity precisely once every 23 hours and 56 minutes. This specific time frame was the absolute key to the mystery. It is the exact duration of a sidereal day, the time it takes for the Earth to complete one full rotation relative to the distant background stars, rather than the Sun. The signal was not coming from the Earth, and it was not coming from our solar system. It was coming from deep space. By meticulously tracking the peak of the hiss, Jansky traced its origin directly to the darkest, most heavily obscured region of the Milky Way in the constellation Sagittarius. Without meaning to, Carl Jansky had accidentally invented the entire field of radio astronomy. More importantly, he had become the first human being to hear the distant, roaring breath of the Leviathan. Jansky's discovery proved that the galactic center was a source of immense, unseen energy, emitting radio waves that easily punch through the 26,000 light-years of cosmic dust. Radio waves, unlike visible light, possess incredibly long wavelengths that allow them to simply roll over the microscopic dust grains completely unimpeded. However, this same physical property creates a severe technological limitation. Because the wavelengths are so long, radio telescopes suffer from terrible resolution. Looking at the galactic center with early radio antennas was like trying to paint a microscopic masterpiece with a giant, thick paint roller. Astronomers could detect a massive, incredibly powerful point source of radio emission, which they designated Sagittarius A star, but they could not see any of the fine details surrounding it. They could not see the stars, they could not see the gas, and they certainly could not prove that the invisible radio source was actually a supermassive black hole. To prove the existence of a black hole, you cannot look at the black hole itself. You must observe how its gravity tortures the physical objects immediately surrounding it. If Sagittarius A star was truly a singular, infinitely dense point of mass weighing millions of times more than our Sun, it would force the stars in its immediate vicinity to orbit at terrifying relativistic speeds. But observing those individual stars required looking at the galactic center in a completely different wavelength of light. Astronomers needed to look in the near-infrared spectrum. Infrared light possesses wavelengths just long enough to slip past the cosmic dust, but short enough to provide the razor-sharp resolution needed to pick out individual stars in the suffocatingly crowded central parsec. But as astronomers built larger and more sensitive infrared telescopes on the ground, they ran into a second, equally infuriating wall of blindness. The enemy this time was not the cosmic dust 26,000 light-years away. It was the Earth's own atmosphere resting just a few miles above their heads. The Earth's atmosphere is a chaotic, churning ocean of varying temperatures and shifting air currents. When the faint, ancient infrared light from the galactic center finally reaches Earth, it must pass through this boiling atmospheric ocean. The light is refracted, bent, and distorted thousands of times a second. This is the same physical phenomenon that causes stars to twinkle to our naked eyes. But for an astronomer trying to measure the exact microscopic position of a star located thousands of light-years away, this twinkling is an absolute disaster. It takes the pinpoint light of a star and smears it into a blurry, overlapping, useless blob. For decades, the greatest infrared telescopes in the world stared at the galactic center and saw nothing but a glowing, unresolved smudge of light. To defeat the atmosphere and finally pierce the cosmic fog, astronomers had to engineer an absolute miracle of modern optical physics known as adaptive optics. In the late 1990s, two rival teams of relentless astrophysicists, one led by Andrea Ghez using the Keck Observatory in Hawaii, and another led by Reinhard Genzel using the Very Large Telescope in Chile, declared war on the atmospheric blur. They equipped their massive telescopes with powerful lasers. They shot these blazing beams of light straight up into the night sky, creating artificial, glowing guide stars high in the upper atmosphere. By constantly monitoring how the Earth's churning atmosphere distorted this artificial laser star, brilliant supercomputers could calculate the exact shape of the atmospheric turbulence thousands of times every single second. These computers then sent lightning-fast signals to a series of microscopic actuators attached to the back of the telescope's secondary mirrors. The mirrors physically deformed, rippling and bending their shape in real time to perfectly counteract the atmospheric distortion. The moment adaptive optics were switched on, the century of blindness came to a violent, spectacular end. The glowing, useless smudge of the galactic center instantly snapped into terrifying, razor-sharp focus. The blurry blob resolved into thousands of individual, fiercely burning stars swarming around the invisible radio source like angry bees defending a hive. Ghez and Genzel had finally acquired the technological eyes necessary to watch the universe play out its most extreme gravitational experiments. For the next 2 decades, these two teams engaged in an unprecedented, excruciatingly patient staring contest with the abyss. They meticulously mapped the positions of the stars in the central parsec year after year, slowly tracing their orbital arcs. Among the chaotic swarm, they isolated a specific group of stars, known as the S-star cluster, that were orbiting dangerously close to the invisible center. And within that cluster, one particular star, designated S2, became the ultimate celestial test subject. S2 is a massive, bright blue star, roughly 15 times heavier than our Sun, and it is trapped in a highly elliptical, terrifyingly fast 16-year orbit around Sagittarius A star. Armed with adaptive optics, the astronomers watched in awe as S2 plunged toward the invisible center of its orbit. As the star approached periaps, the point of closest approach, it accelerated to speeds that simply shatter human intuition. S2 reached velocities exceeding 15 million miles per hour. That is roughly 3% of the absolute speed limit of the universe, the speed of light. At this closest point, S2 was a mere 17 light-hours away from the radio source, a distance only 4 times the gap between our Sun and the planet Neptune. At speeds this extreme, and in gravity this intense, the comfortable classical laws of physics formulated by Isaac Newton begin to violently fray at the edges, and the mind-bending reality of Albert Einstein's general theory of relativity takes the wheel. As S2 whipped around the dark center, astronomers used specialized spectrometers to measure the star's light. They observed a phenomenon known as gravitational redshift. As the photons of light emitted by the star tried to climb out of the unimaginably steep gravitational well, they lost energy. Their wavelengths were physically stretched out, shifting toward the red end of the spectrum. Furthermore, the immense gravity warped the very fabric of space-time so severely that the orbit of S2 did not trace a perfect, closed ellipse. Instead, the orbit itself slowly rotated, tracing a sprawling cosmic spirograph pattern over time, an effect known as Schwarzschild precession. Every single observation, every subtle shift in the star's light, and every agonizingly precise measurement of its trajectory confirmed Einstein's theories with absolute, terrifying perfection. But more importantly, the sheer velocity of S2's orbit provided an undeniable, mathematical proof that ended a century of debate. To force a star as massive as S2 to whip around a hairpin turn at 15 million miles per hour, there had to be an unimaginable amount of invisible mass pulling on it. The calculations were simple, brutal, and absolute. There were exactly 4 million solar masses packed into a region of space smaller than our solar system. In the entire realm of theoretical physics, there is only one entity capable of being that unimaginably heavy and that microscopically small without instantly collapsing in on itself: a supermassive black hole. The monster was real. The century of blindness had officially given way to the era of certainty, a monumental achievement in human history that culminated in Andrea Ghez and Reinhard Genzel sharing the 2020 Nobel Prize in Physics. Yet, as profound as the tracking of S2 was, scientists still craved the ultimate visual confirmation. They wanted to actually see the unseeable. They wanted to capture the silhouette of the event horizon itself. To achieve this seemingly impossible task, the global astronomical community united to create the Event Horizon Telescope. This was not a single physical machine. It was a massive, unprecedented collaboration that linked existing radio observatories situated in the most extreme, remote locations on the planet, from the freezing high-altitude deserts of Chile to the snowy peaks of the Sierra Nevada in Spain, to the absolute frozen desolation of the South Pole in Antarctica. By using atomic clocks to synchronize the data collected from these widely separated dishes with microscopic precision, astronomers utilized a technique called very long baseline interferometry. They effectively synthesized a single virtual radio telescope as large as the entire planet Earth. In May of 2022, the Event Horizon Telescope collaboration unveiled their masterpiece to a stunned global audience. They released the first direct image of Sagittarius A. It was a blurry, glowing, asymmetrical orange ring of superheated plasma surrounding a pitch-black circular void. That dark center was the shadow of the monster, the absolute physical boundary of the event horizon where space and time ceased to function. The image was a monumental triumph of human engineering and international cooperation. It proved, visually and undeniably, that the black hole existed exactly where the orbits of the S-stars dictated it must be. However, as groundbreaking as the Event Horizon Telescope image was, it suffered from a massive limitation of scale. The technique of planetary interferometry provided unparalleled microscopic zoom, allowing astronomers to see the very edge of the abyss. But the field of view was agonizingly small. The image captured a region of space roughly the size of a small coin held at arm's length. It showed the event horizon and the immediate inner rim of the accretion flow, but it was completely blind to the larger environment. It could not see the 10 million stars of the central parsec. It could not see the chaotic, twisting arms of the mini-spirals. It could not see the impossible protostars clinging to life in the tidal zones, nor could it detect the invisible, sinking nomads hiding in the dust. The Event Horizon Telescope gave us a brilliant, blurry snapshot of the monster's mouth, but it could not show us the dark ecosystem in which the monster hunted. This is exactly why the launch and subsequent deployment of the James Webb Space Telescope was the ultimate paradigm-shifting game-changer. Webb was the final key required to completely rip the veil off the galactic center. Unlike the ground-based observatories that fought a desperate, endless war against the Earth's boiling atmosphere, James Webb bypassed the problem entirely. It was launched into a highly specific gravitational pocket known as the second Lagrange point, sitting in the absolute freezing, silent vacuum of space 1 million miles away from our planet. Unhindered by atmospheric distortion, Webb's massive, segmented golden mirrors, stretching 21 feet across, capture ancient infrared light with a resolution and sensitivity 10 times sharper than anything humanity has ever built. Webb combined the dust-penetrating superpower of radio astronomy with the razor-sharp, expansive visual precision of optical telescopes. It did not just zoom in on the event horizon, it pulled back and captured the entire, sprawling, chaotic masterpiece of the central parsec in breathtaking, terrifying high definition. It was Webb that finally revealed the impossible stellar nurseries. It was Webb that mapped the clumpy, violent structure of the bleeding mini-spirals. And it was Webb that detected the chemical signatures of water vapor and the glowing shrouds of the intermediate mass black holes. The century of blindness was over. The fog had been lifted, and the true, incomprehensible complexity of our galaxy's dark heart was finally laid bare. But as Webb's brilliant spectroscopic eyes swept across this newly illuminated landscape, analyzing the atomic and molecular signatures floating in the superheated dark, it detected something deeply unsettling. The prevailing theory, built over decades of observation, was that Sagittarius A star was a quiet, dormant, starving Leviathan. But the chemical anomalies drifting through the central parsec tell a completely different, horrifying story. Webb found the glowing, ionizing scars of a recent, unimaginable slaughter. The quiet state of the monster is a lie. If you are ready to uncover the violent, blood-soaked history of our supermassive black hole and read the absolute forensic evidence left behind by its ancient, catastrophic feasts, make sure you are subscribed and hit the like button. Close your eyes, listen to the static echoing across the cosmos, take a deep breath, and prepare to step out of the light of discovery and directly into the echoing graveyard of an awakened titan. The profound silence of Sagittarius A star, the seemingly starved and dormant state of the 4 million solar mass Leviathan that we observe today, is nothing more than a magnificent temporary illusion. When we look at the galactic center through the golden mirrors of the James Webb Space Telescope or the global network of the Event Horizon Telescope, we are capturing a mere snapshot, a single frozen frame in a cosmic motion picture that spans billions of years. To assume that the black hole has always been this quiet, or that it will remain this quiet forever, is a fundamental failure of cosmic perspective. The interstellar medium surrounding a supermassive black hole is not just a chaotic swarm of gas and stars, it is a canvas, and the black hole is a violently expressive artist. When a black hole feeds, it does not do so quietly. It screams its presence across the electromagnetic spectrum, blasting its immediate environment with sterilizing radiation and kinetic shockwaves. And even after the black hole has finished its meal and returned to its slumber, the scars of that violent feast remain written into the very atomic structure of the surrounding galaxy. To understand the true, terrifying nature of the monster at the heart of the Milky Way, we cannot simply look at the dark shadow of the event horizon. We must become cosmic forensic investigators, sifting through the superheated rubble of the central parsec, looking for the glowing, radiating ghosts of an ancient slaughter. The first undeniable piece of forensic evidence linking our currently quiet black hole to a violently active past was uncovered by the highly sensitive spectrometers of the James Webb Space Telescope. While mapping the chaotic, clumpy architecture of the mini-spirals and hunting for the fragile molecular signatures of water vapor, the mid-infrared instrument detected a glaring, physically impossible chemical anomaly. Drifting through the desolate, seemingly empty spaces between the dense stellar clusters of the central parsec, Webb found massive glowing clouds of ionized neon. Neon, as we understand it on Earth, is a noble gas. It is chemically inert, stable, and fiercely holds on to its orbiting electrons. To ionize neon, to physically rip its electrons away from the nucleus and force the gas to glow with a distinct infrared signature, requires a staggering application of pure energy. Specifically, it requires a localized bath of extreme ultraviolet radiation or highly energetic X-rays, carrying an energy potential exceeding 21 electron volts per photon. In a normal astrophysical environment, the only logical source for this kind of intense, ionizing radiation would be a tight cluster of hyperactive, incredibly hot, newly born stars, such as O-type or B-type giants. These massive stellar furnaces burn so hot that they naturally flood their surroundings with ultraviolet light, ionizing the gas in their immediate stellar neighborhoods. But when astronomers meticulously cross-referenced the location of the ionized neon clouds with the incredibly detailed infrared maps provided by James Webb, the math simply collapsed. There were no hot stars in the vicinity of these glowing neon clouds. The nearest massive stars were located far too distant, their radiant energy falling off according to the inverse square law, rendering them far too weak to effectively strip the electrons from the neon atoms at that specific location. If the stars did not have the energy to violently ionize the neon, there was only one engine in the entire central parsec capable of producing a localized radiation field of that terrifying magnitude, the supermassive black hole itself. But this conclusion immediately presented a glaring paradox. The current, advection-dominated accretion flow of Sagittarius A star, the bloated, superheated cushion of plasma that keeps the black hole starving, is incredibly dim. It currently produces nowhere near the required H of extreme ultraviolet or X-ray radiation to ionize those distant neon clouds. The resolution to this paradox requires us to abandon the concept of the present moment and embrace the physics of deep time. The ionized neon is a ghost. It is a glowing, fading fossil of a catastrophic radiation event that occurred in the past. When a supermassive black hole experiences a massive surge of feeding, it briefly ignites, flooding the central parsec with lethal radiation. This flash of energy instantly strips the electrons from the neon atoms across vast distances. But when the black hole abruptly finishes feeding and goes dark, the neon does not instantly return to its normal state. The vacuum of space is incredibly sparse. It takes a significant amount of time, sometimes centuries or even millennia, for the wandering, stripped electrons to physically find their way back to the naked atomic nuclei and recombine. What James Webb spectrometers are detecting is the slow, agonizing process of cosmic recombination. We are looking at the glowing embers of a cosmic forest fire, the lingering, radiating scars of a massive flare that tore through the central parsec and died out, long before humanity ever had the technological capability to witness it. This chemical ghost story of ionized neon is chilling, but it is not an isolated piece of evidence. It is perfectly corroborated by a completely independent, entirely different branch of astrophysics operating in the high-energy regime of X-ray astronomy. While James Webb observes the warm infrared universe, orbiting observatories like the Chandra X-ray Observatory stare into the absolute highest energy, most violent wavelengths of light. And what Chandra has found echoing through the cold molecular clouds of the galactic center is the undeniable smoking gun evidence of a relatively recent catastrophic awakening. Astronomers utilizing these X-ray observatories rely on a brilliant observational phenomenon known as a light echo. To understand a light echo, imagine standing in a vast dark canyon and shouting as loudly as you can. You will hear your voice bounce off the distant canyon walls, returning to your ears seconds later as an echo. The physics of light operate in a very similar, albeit much faster manner. When a supermassive black hole suddenly consumes a massive clump of matter and violently erupts, it sends a blinding spherical shockwave of X-ray radiation expanding outward in all directions at the absolute speed of light. This initial direct flash of X-rays travels straight toward Earth, and depending on when it happened, it may have already washed over our planet thousands of years ago, completely unnoticed by our primitive ancestors. But not all of that X-ray radiation traveled directly toward us. A significant portion of that expanding sphere of energy traveled sideways, tearing through the dense, frigid molecular clouds that heavily populate the region immediately surrounding the central parsec. These molecular clouds are rich in heavy elements, particularly iron. When a high-energy X-ray photon from the black hole's eruption slams into an iron atom buried deep within a frozen molecular cloud, the iron atom absorbs the energy and immediately violently ejects an electron from its innermost shell. As the atomic structure frantically rearranges itself to fill the void, the iron atom emits a new, secondary X-ray photon. The entire molecular cloud essentially lights up, fluorescing with a distinct characteristic X-ray glow as the invisible radiation front sweeps across it. Because these molecular clouds are located at varying distances from the black hole and at varying angles relative to the Earth, The path the light must travel to reach our telescopes is significantly longer than the direct, straight-line path. The light from the black hole travels out to the cloud, bounces off the iron atoms, and then travels to Earth. This creates a cosmic delay, a light echo that allows astronomers to look directly into the black hole's past. By meticulously mapping these fluorescing iron clouds, watching how they brighten and fade over years of observation, astrophysicists can effectively reverse engineer the geometry of the echoes. They can mathematically trace the bouncing X-rays back to their source, calculating exactly when the original eruption occurred and exactly how powerful it was. The resulting three-dimensional reconstruction of the black hole's history is absolutely staggering. The light echoes perfectly map out a terrifying timeline. They prove that just 300 to 400 years ago, from the perspective of the galactic center, Sagittarius A star was not sleeping. It was violently, aggressively awake. It was erupting with an X-ray luminosity that was at least 1 million times brighter than the quiet, starving baseline we observe today. To put that timeline into a human perspective, roughly around the exact same time that the Italian astronomer Galileo Galilei was pointing his primitive handcrafted optical telescope at the sky for the very first time, completely blind to the existence of galaxies, the supermassive monster at the center of our Milky Way was actively detonating, flooding the inner galaxy with a sterilizing storm of high-energy radiation. The silence we see today is a profoundly recent development. The black hole is merely digesting a meal it consumed during the Renaissance, yet a million-fold increase in X-ray luminosity 400 years ago, while catastrophic for anything in the immediate vicinity of the central parsec, is still just a minor hiccup in the grand scale of supermassive black hole physics. It represents the consumption of a large asteroid or perhaps a small gas cloud. To see the true, incomprehensible scale of the Leviathan's wrath, to witness the absolute zenith of its destructive capability, we must completely zoom out. We must leave the suffocating confines of the central parsec, leave the chaotic swarms of the inner spiral arms, and look at the entire Milky Way galaxy from the outside, utilizing the most extreme, energetic spectrum of light in the universe, gamma rays. In the year 2010, scientists operating the Fermi Gamma-ray Space Telescope made a discovery so massive, so structurally profound, that it forced a complete rewrite of the Milky Way's anatomical map. Staring through the galactic plane, peering deep into the empty, desolate halo of space located directly above and below the galactic center, the Fermi telescope detected two colossal, perfectly symmetrical lobes of high-energy radiation. These structures, now known as the Fermi bubbles, are unimaginably vast. They protrude directly out of the galactic center, inflating upward into the northern galactic hemisphere and downward into the southern galactic hemisphere. Each bubble stretches for an astonishing 25,000 light-years. Combined, this hourglass-shaped structure of glowing gamma-ray and X-ray radiation spans 50,000 light-years from tip to tip. It is a structure roughly half the diameter of the entire Milky Way galaxy itself, completely invisible to the naked eye, yet dominating the sky in the realm of high-energy physics. To understand what the Fermi bubbles are, you must imagine them as the ultimate cosmic exhaust fumes. They are filled with an incredibly tenuous, low-density plasma that has been heated to tens of millions of degrees, swirling with hyper-accelerated cosmic rays and tangled magnetic fields. The sheer physical energy required to inflate a structure of this incomprehensible magnitude is mathematically staggering. It requires an injection of kinetic and thermal energy equivalent to millions of massive stars simultaneously exploding as supernovae, all concentrated in the exact center of the galaxy within a relatively short time frame. While the dense stellar clusters of the central parsec do experience a high rate of supernova detonations, the math simply does not add up. Even the combined continuous explosions of the hyperactive Wolf-Rayet stars and the violent collisions of the stellar demolition derby cannot account for the sheer focused power required to blow a 50,000 light-year bubble into the intergalactic medium. There is only one engine in the Milky Way capable of acting as the pump for this galactic-scale inflation. The Fermi bubbles are the ultimate, undeniable relic of an era when Sagittarius A star entered a full, rampant, tyrannical feeding frenzy. This was not a minor flare or the ingestion of a stray asteroid. Millions of years ago, the supermassive black hole was not an Invection-dominated starving sleeper. It was a fully realized, blazing, active galactic nucleus. A massive, catastrophic influx of matter, perhaps the dense, gas-rich core of a cannibalized dwarf galaxy, or an unusually massive molecular cloud containing hundreds of thousands of solar masses, plunged completely past the thermal cushion and flooded the inner accretion zone. Faced with this sudden, overwhelming glut of fuel, the black hole choked. The accretion disk became so incredibly dense, so insanely hot, and spun with such terrifying velocity that the magnetic fields threading through the plasma became wound infinitely tight. These twisting, screaming magnetic field lines were forced into tight, vertical funnels at the exact north and south poles of the black hole's rotation. These magnetic funnels acted as the most powerful particle accelerators in nature. They gathered the superheated, ionized plasma that could not fit across the event horizon and violently launched it outward, blasting it away from the black hole at velocities approaching the absolute speed of light. These twin relativistic jets acted like cosmic blowtorches. They drilled straight up and straight down, punching directly through the dense, suffocating gas of the galactic plane, violently clearing a path and erupting out into the empty, desolate halo of the Milky Way. For hundreds of thousands, perhaps millions of years, these jets roared continuously, pumping unimaginable quantities of kinetic energy, superheated plasma, and cosmic rays into the void, slowly inflating the magnificent, terrifying Fermi bubbles that we observe today. When we look at the ionized neon, the X-ray light echoes, and the colossal majesty of the Fermi bubbles, a chilling, undeniable realization takes hold. The supermassive black hole at the center of our galaxy is not a passive, dying star, slowly fading into irrelevance. It is a hibernating apex predator. The entire history of the Milky Way is punctuated by these catastrophic, cyclical awakenings. The monster feeds, it roars, it blasts the galaxy with sterilizing radiation and inflating jets of plasma. And then, as the fuel supply runs dry, it returns to its Invection-dominated slumber. The profound silence we are observing today, the delicate, impossible protostars being born in the tidal zones, the quiet drifting of the intermediate mass black holes, all of this is nothing more than a temporary, fleeting intermission. We are merely living in the quiet, breathless space between two violent heartbeats. And the most terrifying question in modern astrophysics is not whether the monster will wake up again, but when. Because as we stare into the chaotic, swarming demolition derby of the central parsec, we can clearly see that the alarm clock is already ticking. There are massive, doomed objects currently plunging down the steepening gravitational well, moving on a direct, unavoidable collision course with the sleeping Leviathan. The ingredients for the next ignition are already in motion. If you want to know exactly what is falling into the abyss and what will happen to the galaxy when the monster inevitably opens its eyes, subscribe to the channel, hit the like button, and brace yourself. We are about to map the anatomy of an ignition and witness the terrifying mechanics of a supermassive awakening. The profound silence we observe today from the supermassive black hole at the heart of our galaxy is a fragile, temporary state. It is the quiet, breathless pause between the violent, catastrophic heartbeats of an apex predator. The Leviathan is starving, trapped behind its own bloated cushion of superheated plasma. But it is not dead. It is waiting. And within the chaotic, hyperactive demolition derby of the central parsec, where 10 million stars scream through the void at millions of miles per hour, the cosmic alarm clock is already ticking. The chaotic gravitational interactions of the stellar swarm guarantee that the current starvation diet cannot last forever. There are massive, doomed objects currently plunging down the steepening gravitational well, moving on direct, unavoidable collision courses with the absolute boundary of destruction. The ingredients for the next grand ignition are already in motion, locked in a fatal orbital dance that we are watching play out in real time from our distant vantage point on Earth. To understand how the sleeping giant will inevitably awaken, we must trace the harrowing journeys of the celestial objects that are currently flirting with the abyss. For over a decade, the global astronomical community held its collective breath as they tracked the terrifying trajectory of a specific enigmatic object designated simply as G2. Discovered in 2011 by the same relentless teams operating the Very Large Telescope in Chile, G2 initially appeared to be a massive, incredibly dense cloud of ionized hydrogen gas and dust, roughly 3 times the mass of our planet Earth. By meticulously plotting its orbital path, astronomers realized with mounting excitement that G2 was not trapped in a safe circular orbit. It was on a highly eccentric, plunging trajectory that was aiming directly at the immediate vicinity of Sagittarius A star. The mathematics were stark and undeniable. In the summer of 2014, G2 was scheduled to reach periaps, the absolute closest point in its orbit to the 4 million solar mass monster. At this closest approach, the cloud would pass within a mere 260 astronomical units of the event horizon. To put that into perspective, it is a distance roughly equivalent to only 6 times the orbital radius of Pluto. In the realm of supermassive black holes, that is a microscopic, suicidal shave. Astronomers around the world prepared for a spectacular, violent astronomical show. According to the classical laws of astrophysics, a mere cloud of gas and dust passing that incredibly close to a supermassive black hole should have been entirely doomed. The sheer mechanical power of the black hole's tidal forces should have been overwhelming. The gravity pulling on the leading edge of the G2 cloud would be immensely stronger than the gravity pulling on its trailing edge. This severe gravitational gradient was expected to aggressively stretch the cloud, tearing it apart and shearing it into a long, glowing ribbon of plasma. As the shredded remains of G2 spiraled inward and slammed into the hot, bloated accretion flow, it was predicted to trigger a massive, spectacular feeding event. Telescopes across the entire electromagnetic spectrum, from radio antennas to X-ray satellites, were all locked onto the galactic center, waiting to record the sudden, violent flare of an awakening titan. But the universe, as it so often does in the central parsec, defied human expectations. The summer of 2014 arrived. The G2 object screamed through its closest approach, enduring the absolute maximum intensity of the black hole's tidal shear, and the astronomical community watched in stunned silence. There was no catastrophic fireworks display. There was no massive X-ray flare. The supermassive black hole remained agonizingly quiet. When the object emerged from the far side of its harrowing orbital plunge, the high-resolution infrared instruments of the Keck Observatory and the Very Large Telescope revealed something impossible. G2 had been stretched, distorted, and violently elongated by the immense gravity, but it had not been destroyed. It remained structurally cohesive, continuing along its orbit as a distinct unified object. The survival of G2 forced a complete, rapid reassessment of what exactly was plummeting toward the black hole. A simple, unstructured cloud of gas could never have survived that level of tidal stretching. The only physical explanation for its survival is that G2 is a wolf in sheep's clothing. Hidden deep within that glowing, dusty envelope of gas, completely obscured from our infrared sensors, there must be a dense, incredibly heavy stellar core. It is likely a binary star system that recently collided and merged, producing a bloated, dusty, newly formed star. The immense self-gravity of this hidden stellar core fought a desperate localized war against the tidal pulling of the supermassive black hole. As the black hole tried to tear the dusty envelope away, the hidden star's own gravity aggressively pulled the material back together, holding the object intact through the most dangerous segment of its journey. The Leviathan was essentially teased. A meal was dangled mere astronomical units from its jaws, only to be snatched away by the localized gravity of a hidden, massive core. While G2 managed to survive its terrifying plunge, its survival merely delays the inevitable. The central parsec is a numbers game, a statistical certainty of impending doom. With millions of stars packed into a space where only one should exist, their chaotic, intersecting orbits constantly perturb one another. Every single day, stars are gravitationally nudged, bumped, and kicked by their neighbors. Eventually, through the sheer mathematical inevitability of the demolition derby, a star will be knocked off its stable trajectory. It will not be a dusty, cohesive core like G2. It will be a standard burning main sequence star, and it will be sent on a fatal plunging trajectory that crosses the absolute threshold of no return, the tidal disruption radius. When a typical star, a massive sphere of fusing plasma, crosses this invisible mathematical boundary, it does not simply fall into the black hole. The sequence of events that follows is one of the most violent, spectacular, and completely destructive processes in the known universe, an event astronomers coldly refer to as a tidal disruption event. As the doomed star crosses the threshold, the gravitational gradient of the 4 million solar mass black hole becomes so profoundly steep that the star's own internal gravity, the force that has held it together as a perfect burning sphere for billions of years, is completely overwhelmed. The star physically loses the ability to hold onto its own plasma. In a matter of hours, the spherical shape of the star is brutally deformed. It is violently stretched along its orbital path and simultaneously compressed from the sides, elongating into the shape of a colossal cosmic cigar. As it plunges deeper, the tidal forces intensify exponentially, and the star is literally ripped inside out. The immense nuclear furnace at its core is exposed and extinguished, and the entire mass of the star is unspooled into a searing, continuous river of superheated plasma. Astronomers call this horrifying, mechanical dismantling spaghettification. Once the star is completely unspooled into a flowing river of stellar guts, the true awakening begins. The leading edge of this plasma river whips around the backside of the black hole at significant fractions of the speed of light. As it completes its initial orbit, it violently crashes into the trailing edge of its own stream. This self-intersecting collision is cataclysmic. Millions of tons of superheated plasma slam into each other at relativistic speeds, instantly converting their immense kinetic energy into a blinding, staggering flash of thermal radiation. The plasma is instantly heated to hundreds of millions of degrees, far hotter than the bloated advection flow that normally surrounds the black hole. This sudden, overwhelming injection of dense, unimaginably hot plasma shatters the delicate, starving equilibrium of the black hole. The bloated, inefficient thermal cushion is completely overwhelmed by the sheer mass of the shredded star. A new, violently active, incredibly dense, and razor-thin accretion disk forms almost instantaneously. The black hole transitions from a starving, quiet sleeper into a roaring, actively feeding monster. For months, and possibly even years, the galactic center blazes with an intensity that defies comprehension. The feeding frenzy produces a sustained, blinding torrent of X-rays, extreme ultraviolet light, and gamma radiation that punches through the surrounding environment, completely outshining every other source of energy in the central parsec combined. The consequences of this awakening for the surrounding galactic ecosystem are absolute and apocalyptic. The central bulge of the Milky Way, the dense spherical concentration of stars extending several thousand light-years outward from the black hole, is transformed into a highly lethal radiation zone. If there are planetary systems orbiting the stars within this inner region, and if those planets harbor any form of complex, delicate biology, the awakening of Sagittarius A star spells their absolute eradication. The initial blast of extreme ultraviolet and X-ray radiation would hit these inner planets with the force of a cosmic blowtorch. The high-energy photons would violently strip away their protective atmospheres, boiling away any surface oceans and heavily irradiating the barren rock left behind. But the radiation is only the first wave of the apocalypse. The violently spinning, hyperactive accretion disk of the newly awakened black hole acts as an unparalleled particle accelerator. It generates unimaginably powerful, twisting magnetic fields that grab protons and atomic nuclei from the shredded star and violently launch them outward at 99.9% the speed of light. These are cosmic rays, and an active supermassive black hole produces them in staggering, lethal quantities. When a storm of these relativistic cosmic rays washes over a planet, they do not just burn the surface, they penetrate deep into the cellular structure of any surviving organic matter. They act as microscopic bullets, violently shattering the delicate bonds of DNA, causing rampant, catastrophic mutations and unraveling the very biological code of life. The inner few thousand light years of the Milky Way galaxy are not a safe harbor. They are a cyclical death zone, routinely sterilized by the inevitable, violent feeding frenzies of the central Leviathan. Yet, as we contemplate the sheer, terrifying scale of this planetary sterilization, we must recognize the profound, incredible luck of our own cosmic positioning. The Earth is not located in the crowded, irradiated death zone of the central bulge. We are perched out in the quiet, desolate suburbs, a staggering 26,000 light-years away from the monster's jaws. This immense, unfathomable distance is our ultimate, unbreakable cosmic shield. By the time the blinding X-rays and the lethal storms of cosmic rays traverse the 26,000 light-years of space to reach our solar system, their intensity is vastly diluted, spread out over an expanding spherical volume that weakens the radiation according to the strict, unforgiving geometry of the inverse square law. Furthermore, the very thing that kept humanity blind to the black hole for almost our entire history now acts as our greatest physical protector. The Great Rift, that towering, impenetrable 26,000 light-year-long wall of freezing molecular gas and microscopic silicate dust, stands directly between us and the galactic center. When the supermassive black hole inevitably detonates, sending its sterilizing wave of extreme ultraviolet and X-ray radiation screaming toward Earth, those high-energy photons will slam into the dust wall. The dust grains will absorb the lethal radiation, physically stopping the death ray in its tracks. The dust will heat up, violently absorbing the energy, and then slowly, safely re-radiate that energy out into the galaxy as harmless, warm, infrared light. If Sagittarius A star were to completely shred a massive star tomorrow and awaken into a blazing active state, the residents of Earth would be in absolutely no physical danger. Our atmosphere would not boil, our oceans would not evaporate, and our DNA would not unravel. The only noticeable change for humanity would be in the night sky. If you looked up at the constellation Sagittarius with the naked eye, you might notice that the dark patches of the Milky Way seem to be glowing with a faint, eerie, reddish warmth, as the heated dust wall safely absorbs the apocalypse. Radio astronomers and X-ray observatories in orbit would go absolutely frantic, recording the greatest astronomical event in human history. But down on the surface, life would continue completely undisturbed. The sheer, terrifying scale of the galaxy, the very thing that makes us feel so small and insignificant, is the exact physical mechanism that guarantees our survival. Distance is our greatest blessing. But there is a profound, unsettling temporal philosophy attached to this vast distance. Because the speed of light is the absolute speed limit of the universe, the light and radiation from the galactic center take exactly 26,000 years to reach our telescopes. This means we are permanently trapped in the past. We are never observing the black hole as it exists right now. We are watching a ghost, a delayed broadcast of an ancient reality. When James Webb stares at the clumpy mini-spirals and the drifting intermediate mass black holes, it is looking at the galactic center as it existed 26,000 years ago. When that light began its journey toward Earth, human beings were still living in the depths of the last ice age. We were hunting woolly mammoths with stone-tipped spears, completely unaware of the universe beyond the horizon. This absolute temporal delay means that the cosmic alarm clock may have already gone off. A massive star may have already crossed the tidal disruption radius. The Leviathan may have already been violently awakened, its accretion disk blazing with the light of a shredded sun, sending a tidal wave of radiation expanding outward through the dust. If the black hole ignited 10,000 years ago, the initial flash of X-rays is currently racing through the Orion Spur, completely invisible, entirely silent, and still 16,000 years away from reaching our detectors. We live in a perpetual state of cosmic suspense, constantly analyzing the ancient light for any sign that the monster has already opened its eyes. We can never know the present. We can only wait for the past to finally arrive. Yet, while the sudden, violent awakening of a tidal disruption event remains a terrifying, unpredictable surprise hidden by the delay of light, it is ultimately just a minor, localized flare-up in the grand, sweeping narrative of the cosmos. The Milky Way will survive a feeding frenzy. The black hole will eventually consume the shredded star, run out of fuel, and return to its advection-dominated slumber. But as we pull our perspective back even further, leaving the confines of the Milky Way entirely and looking out into the pitch-black void of the local galaxy group, we can see a much larger, absolutely inescapable doom racing toward us. The monster in our basement is not the only Leviathan in the dark. There is another, much larger apex predator approaching, and it is bringing its entire galaxy with it. If you have journeyed with me this far into the terrifying mechanics of black holes and the illusion of cosmic time, do not stop now. Hit subscribe, leave a like, and brace yourself for the final chapter. The long, quiet isolation of the Milky Way is coming to a violent end, and the ultimate convergence is about to begin. As we pull our perspective back from the localized, violent feeding frenzies of Sagittarius A star and the agonizingly slow delay of the cosmic light bringing us its history, we must confront a truth that is far more absolute and far more terrifying than a simple tidal disruption event. The Milky Way galaxy, for all of its staggering immensity and its hundreds of billions of stars, is not a static, isolated island floating peacefully in the dark. It is a physical object bound by the inescapable tyrannical laws of gravity, and it is currently locked in a fatal head-on collision course with an apex predator that dwarfs our own. This is not a theoretical possibility or a distant abstract mathematical model. It is an astronomical certainty. To understand the ultimate fate of our supermassive black hole and the final violent chapter of the galaxy that birthed us, we must cast our gaze 2.5 million light-years outward into the freezing, empty expanse of the intergalactic void, toward the constellation of Andromeda. Getty Images. Fa. Hovering in the deep, pitch-black ocean of the local group of galaxies is the Andromeda Galaxy, also known to astronomers as Messier 31. It is a magnificent, sprawling spiral galaxy that is significantly larger, more massive, and far more densely populated than the Milky Way. And it is not moving away from us with the general expansion of the universe. Because our two galaxies are relatively close to one another in the cosmic scale, their mutual gravitational attraction has completely overpowered the expanding fabric of spacetime. Andromeda is currently falling directly toward the Milky Way at a staggering velocity of 250,000 miles per hour. Every single second that passes, this gargantuan island of 1 trillion stars closes the distance between us by nearly 70 miles. For the next 4 to 5 billion years, the night sky of our solar system, assuming the Earth or its descendants still exist to witness it, will undergo a terrifying and majestic transformation. Andromeda will grow from a faint, fuzzy smudge in the northern hemisphere into a blinding, overwhelming wall of stellar fire that consumes the entire field of view. The collision of two massive spiral galaxies is not a sudden, violent crash of solid objects, because the distances between individual stars are so unimaginably vast. The actual stars themselves will almost never physically collide. They will pass right through one another like two swarms of glowing ghost bees. But the galaxies are not just made of stars. They are filled with immense, sprawling oceans of cold molecular gas and surrounded by massive, invisible halos of dark matter. When these vast oceans of interstellar gas finally slam into one another, the true violence of the convergence will begin. The sheer kinetic friction of the colliding gas clouds will generate colossal shockwaves that ripple across hundreds of thousands of light years. These shockwaves will aggressively compress the hydrogen gas, triggering a frantic, galaxy-wide firestorm of star formation. Millions of new, massive, brilliantly blue stars will ignite simultaneously, illuminating the chaotic, distorted wreckage of the two spiral arms. The elegant, organized, spinning pinwheel structures of both the Milky Way and Andromeda will be completely shattered. Their gravitational fields will tangle, violently ripping long, glowing tails of stars and gas out into the intergalactic void. Over hundreds of millions of years, the two distinct galaxies will lose their identities entirely, blurring and churning together into a single, chaotic, amorphous blob of stellar mass that astronomers have already preemptively named Milkomeda. But while the stars dance and the gas clouds burn in a chaotic, sprawling ballet, a much darker, far more absolute drama will be unfolding deep within the suffocating core of this newly forming supergalaxy. The two supermassive black holes, the gravitational sovereigns of their respective realms, will be orphaned. Sagittarius A star, with its 4 million solar masses, will finally meet its superior. The supermassive black hole at the center of the Andromeda Galaxy is a true heavyweight, estimated to weigh at least 100 million times the mass of our Sun. It is 25 times more massive and infinitely more powerful than our own starving Leviathan. As the two galaxies merge, the exact same physical mechanism of dynamical friction that drags the invisible, intermediate mass black holes down into the central parsec will begin to operate on an apocalyptic, galactic scale. The two supermassive black holes will plow through the newly combined, hyperdense stellar core of Milkomeda. Their immense gravity will tug at the surrounding millions of stars, creating massive trailing wakes of stellar density that pull backward on the black holes, sapping their orbital momentum. Stripped of their original galactic centers, the two Leviathans will begin a terrifying, inescapable death spiral toward one another. They will sink to the very absolute bottom of the new gravitational well, destined to share the exact same microscopic point in space. For millions of years, they will orbit each other in a dark, silent binary system. As they draw closer together, their combined gravitational pulling will act as an unparalleled cosmic blender. Any stars or gas clouds unfortunate enough to be trapped in the immediate vicinity of this binary monster will be violently shredded, creating a chaotic, swirling, shared accretion disk of superheated plasma that feeds both black holes simultaneously. The newly formed Milky Way galaxy may briefly ignite as the most brilliant, terrifying quasar in the local universe, its dual engines roaring with the consumed wreckage of two shattered galaxies. But eventually, the gas will be consumed or blasted away, and the two supermassive black holes will be left alone in the dark, orbiting one another at distances measured in mere light months, then light days, and finally light hours. At these incredibly intimate relativistic distances, dynamical friction against the surrounding stars ceases to be the primary mechanism draining their energy. The environment changes, and the fundamental laws of Albert Einstein's general relativity take total, absolute control. As the two black holes whip around each other at significant fractions of the speed of light, their staggering combined mass violently churns the very fabric of space and time. Imagine dragging two incredibly heavy bowling balls in a rapid circle across a tightly stretched trampoline. The fabric of the trampoline will buckle, warp, and send deep, rolling vibrations spreading outward in all directions. In the vacuum of space, this distortion manifests as gravitational waves. These are literal physical ripples in the geometry of the universe itself. As the black holes accelerate in their tightening death spiral, they churn the space-time continuum, bleeding away immense quantities of their orbital kinetic energy by radiating it outward as pure gravitational waves. Because they are constantly losing energy to these invisible ripples, their orbit decays faster and faster. The spiral becomes a plummet. In the final, agonizing thousands of years, the emission of gravitational waves reaches a shrieking, chaotic crescendo. The black holes are moving so fast, and their event horizons are so close, that the space between them becomes a violently unstable, physically unnavigable maelstrom. And then, the ultimate convergence occurs. The exact moment the two event horizons physically touch is an event of such profound, unadulterated violence that it completely breaks the human capacity for visualization. In a fraction of a millisecond, the two black holes merge into a single, seamless, ultramassive entity. But this merger is not a quiet addition of mass. In that microscopic fraction of a second, an amount of mass equivalent to several million of our suns is instantaneously and completely erased from the physical universe. It is violently converted into pure, unadulterated energy, adhering to the absolute brutality of Einstein's famous equation E equals mc squared. This energy is not released as visible light or X-rays or gamma radiation. it is released entirely as a single apocalyptic burst of gravitational waves. For that one fleeting fraction of a second, the gravitational scream of this merger will literally outshine the combined optical light of every single star in every single galaxy across the entire observable universe. It is the loudest, most violent, and most powerful event possible in the cosmos, short of the Big Bang itself. The fabric of space and time will ring like a struck bell. The gravitational waves will blast outward from the core of Milky Way at the absolute speed of light, violently stretching and compressing the space between atoms, between planets, and between stars as they pass. If you were standing on a planet relatively close to this merger, the physical stretching of the space containing your body would be so severe that you would be instantly torn apart, not by a physical force, but by the geometry of the universe expanding and contracting inside of you. But by the time those waves travel across the millions of light years to whatever distant galaxies lie beyond, they will have faded into microscopic, subatomic vibrations, destined to wash over the advanced gravitational wave detectors of whatever alien civilizations are currently pointing their instruments at the dark, waiting to hear the echoes of colliding titans. When the screaming of space-time finally stops and the gravitational ripples fade away into the expanding void, the violent, chaotic era of the Milky Way, and Andromeda will be permanently over. The newly forged, singular, supermassive black hole, now weighing over 104 million solar masses, will undergo a brief, vibrating phase known as ringdown, physically settling into its new, perfect spherical shape. It will sit at the exact, silent center of a massive, featureless, elliptical galaxy. The beautiful spiral arms will be gone. The frantic, high-speed demolition derby of the central parsec will be smoothed out into a massive, slow-moving swarm of aging, cooling, red stars. The great cosmic engine will run out of fuel, the remaining gas will be exhausted, and the new Leviathan will enter a permanent, eternal slumber, reigning over a quiet, fading galaxy until the end of time itself. This is the ultimate, inescapable destiny of our supermassive black hole and the galaxy that surrounds it. It is a story of profound violence, of crushing gravity, of blinding flares, and of screaming space-time. But as we pull back from the terrifying vastness of this billion-year vision and return to our present moment, sitting on our tiny, fragile blue world in the quiet suburbs of the Orion Spur, we are left with a staggering, almost overwhelming sense of philosophical connection. We are not separate from the violent mechanics of the galactic center. We are the direct physical byproduct of it. The very atoms that compose your body, the iron in your blood that carries oxygen to your brain, the calcium that forms your bones, and the carbon that builds the cellular structure of your heart, none of these elements were created in the Big Bang. They were forged in the absolute, crushing nuclear furnaces of massive stars. And the life cycle of those stars, their birth in the collapsing molecular clouds, their chaotic, high-speed orbits, and their violent, explosive deaths as supernovae, are all intimately, permanently dictated by the gravitational rhythm of the supermassive black hole. The cosmic rays launched by the Leviathan's ancient feeding frenzies likely influenced the mutation rates of early single-celled organisms on Earth, subtly steering the chaotic, branching path of biological evolution. The heavy elements blasted out of the central parsec by the apocalyptic shock waves of the Fermi bubbles slowly drifted across the galaxy for billions of years, eventually seeding the cold, dark molecular cloud that would collapse to form our sun, our planet, and ultimately us. We are the universe experiencing itself. We are a temporary, incredibly brief configuration of stardust, granted the astonishing, fleeting ability to look back at the dark, beating heart of the machine that built us. When the James Webb Space Telescope peers through the 26,000 light-years of cosmic fog, capturing the faint, glowing signatures of impossible protostars and the radioactive scars of ancient slaughters, it is not just taking a picture of a distant, abstract object. It is taking a picture of our origin. It is showing us the chaotic, violent, and unfathomably beautiful forge of creation, The monster at the center of the Milky Way sleeps, but its dreams are written into the very fabric of our existence. Its ancient roars echo in the atoms of our planet, and its future awakening will determine the ultimate fate of the stars in our sky. We live in the quiet, breathtaking pause between the heartbeats of gravity and silence. We are ghosts of the cosmos, drifting through the dark, trying to understand the Leviathan before the great convergence inevitably arrives. If this journey into the dark heart of the Milky Way has shifted your perspective of the universe and our fragile place within it, if you felt the crushing weight of gravity and the terrifying expanse of deep time, please leave a like on this video and share it with someone who needs to look up at the night sky with a new sense of wonder. Make sure to subscribe to the channel and hit the notification bell, because the universe is filled with infinite, terrifying mysteries, and we are just beginning to scratch the surface of the dark. Leave a comment down below and tell me what cosmic phenomenon you want us to explore next. Until then, keep your eyes on the stars, embrace the silence of the void, and never stop questioning the beautiful, chaotic mechanics of our cosmic home. Sleep well, and I will see you in the next exploration.